I have a few hours to do group theory, a lot of it, and I will be doing marathon. I have done like a few of these questions. I've never been so locked in for an exam other than extra pure. Just for context, I do OCMEI further maths, and one of my additional modules is extra pure further maths, which includes very, very exciting topics from recurrence relations, multivariable calculus, um, eigenvalues, eigenvectors, and finally group theory. Group theory is the most novel mathematics that people will encounter at sixth form, and I'm quite privileged to have learned group theory in sixth form, especially because I want to go into a pure maths degree. But aside from talking random things, I'm just going to start with the first question, which I did. Um, so this is a whole booklet of like um, a lot, a lot of group theory questions. They've been collated by my friend and I, and took a long time. But um, just to start, you're given a Cayley table. Amazing. Um, Very first part, verify QST and is equal to QST. So just checking associativity. Second part is to show that this forms a group. The first thing I do is just see if there is any if the Latin square properties are are there. But because they say prove that a set this is a group, I'm not going to bother checking. I'm just going to say the table shows closure. And then lastly, we need to find an isomorphic group to actually no, we just need to list down the elements of this isomorphic group to G. The first thing to note is that this is a group of order 5, and up to isomorphism, there is only one unique group, which means that every group of order 5 is isomorphic to each other. And that's very helpful to know because that the only group that exists that is order 5 is a cyclic group. And that's going to be very important for part 3. So part 1, I already marked this as well. QST, I mean, if we look at the table, I mean, it's quite obvious. You do first ST, ST is P, then QP is S, QS is T, and TT is S. And then you say left-hand side is equal to right-hand side. Second part of this, again, the group axioms I need to prove are closure, invert, every element has an inverse, there's an identity element, and associativity, but we are told to assume associativity holds. So composition table shows closure, that's enough. There is an identity element, which is R. You can kind of see that this row and this row is left preserved. Now, for to show inverses, what I did do is list out all the elements and then wrote down the inverses, which is fine. Then state that every element has an inverse, and then just a short conclusion. There is a second method I want to do as well, specifically because this is a group 5 order 5 group, but I'll get to that. Now, this is just a general cyclic group. D is the generator, and that's 2 marks, easy 2 marks. But a second method to show that this is a group is to find a generator. We know that it's order 5, that means there must be a generator if it's a group. And I mean, if you exclude the obvious, which is R, let's see P. P, I'm gonna call the operation, actually, no. PP is T, TP, TP is Q. It doesn't really matter what order I do because every cyclic group is abelian, so it's commutative. So I could write PT or TP, doesn't matter. But regardless, Q, P is S, SP is S, P is R, and we've reached our identity. So p squared, p cubed, p to the 4, and p to the 5, they generate the set PQRST. And I think that should be enough to show this is a group, because you have a generator, it produces a closed group as well. Sorry, closed set under the operation. And yeah, next question, which I didn't get to finish, I don't even know if it's right. You have set S consisting of numbers 3 to the n, where n is an integer. Prove that the elements of S under multiplication form a commutative group. So just an abelian group. And then we're given a few cases, and we need to say whether each of these are a group or not. The first part should be straightforward. I think it's the extra marks because we have to show it's commutative. I think the biggest trap here is that they say that we can assume addition of integers is associated with commutative, not the operation of the group itself. So closure, that's fine for all mn that are integers. 3 to the n times 3 to the m is 3 to the n plus m for indices laws, and that is part of S. Identity, you can't just go assume 3 to the 0, because you have to show that this is the identity. And the way to do that is you do 3 to the n times your identity element. I could have just written e here, to be fair, or 3 to the e, I don't know. Actually, now that I'm thinking about it, it would be probably better if I wrote. Let me get a different pen. If I wrote 3 to the n times e is equal to e times 3 to the n, which is 3 to the n. And from here, it's obvious e is equal to 1. Let me this ugly one. And then inverses, same process. You call your whole thing the inverse of 3 to the n, this with the minus 1, and then you just show it's 3 to the minus 1. You can't just go straight to assume it's minus 1. You need to show the steps. Associativity, which is always annoying to show. This is your left hand side, this is your right hand side. If this holds, again, here is where the addition of integers associative and commutative helps. And commutativity is the last one. Again, this is where it's helpful to assume the addition of integers is commutative. And because all 4 group axioms are satisfied, this is an abelian group. So it's a commutative group. Now, for the first case, if I'm not wrong, is 3 to the n, n is an integer. Is that right? 3 to 2n, I think. Yeah, 3 to n. Yeah, okay. 3 to 2n. I don't know why this wouldn't be a group. It would just be a subset, a subgroup of G. For the next part, 3 to the n is greater or equal to 0, n is an integer. Now, the inverse of 3 to the n is 3 to the minus n. Minus n is not part of this, is less than 0, which means it does not exist. And if an element does not have an inverse, then the set under the operation cannot be a group. Now the last one, I'd say it's a group, but I'm not sure. It's 2 marks. I don't know what I have to show everything, but I'm going to say same as A. Just quickly, I'm going to check the mark scheme, which is kind of annoying because I didn't collate the mark schemes. I just collated papers. So I'm going to be very quick. That was, and I'm going to try and screenshot it and put next there. Okay. Hopefully it can be seen. So showing closure, okay, that's fine. Consider associativity, okay. you always have to consider three distinct elements: stating the identity, the inverse, and commutative. Okay, I would get all 6 marks, I think. Yeah, I mean, I would have to show identities and inverse, okay, and closure. So you basically have to pre-prove that it's a group. I just think it's silly for 2 marks. Yes, so B isn't a group. Okay, so C is not a group. Why? Because it's not closed. Oh right. Oh yeah, because yes. So that's a good counterexample. I did not think of that. 3 to the 2 is 3 to the 5, which is not in the form of n squared. It's not a square number. Um, oh, okay. N squared plus n squared is equal your indices. That does not mean it's not equal to k squared always. Okay, fair enough, fair enough. So I would not get those marks. Good that I checked. Okay, next question. 1 second. Okay, next question. A group G of order 6 has the combination table below. State with a reason whether or not G is commutative. State the number of subgroups of G which are order 2. List the elements of the subgroup of G which is of order 3. And then lastly, a multiplicative group H of order 6 elements, those where E is identity, write down the order of each element C3, C4, C5. Now, I think, so because it's order 6, this can either be abelian. If it's abelian, then it's a cyclic group. I think it's C6 or C3? C6, I think. Or if it's non-abelian, then this is the dihedral group 3, which is just the symmetries of a triangle. Or I think this is isomorphic to the alternating group 3, but don't quote me on that. I'm pretty sure it is isomorphic to the group of the alternating group of 3 permutations. Okay, so that's good to know. So again, if it's abelian, then we can see that there is symmetry along this main diagonal. And there clearly is symmetry along this main diagonal. So, yes, it is commutative because there is symmetry along the main diagonal, which shows that PQ is equal to QP. I think just stating that from the Cayley table should be enough. Which if it is abelian, then it must be a cyclic group. State the number of subgroups of G which are of order 2. Okay, that's a good one. So I'm gonna go down here. For my part A, I'm going to say from Cayley table, there is symmetry along the main diagonal, which implies that it is commutative, which is abelian. Then we can say for part 2, we can say for part 2, that state the number of subgroups of G which are of the 2. Well, if let's say E is the identity, so I can't use that. If A is the generator, then a subgroup of order 2 is going to be a to the 3 and e, which is the identity, and a to the 3 is equal to, let me find this, a b, and then ba is e. Okay, a is not going to work because a is order 3. Let me try b then. Um, b b squared is what? B squared is a, so that's not going to work. Oh, actually, q. Yes. I'm actually an idiot. You can tell from the KD table immediately that actually yes, it's bad. That Q is a self-inverse because Q is that Q? No, that's a P. Sorry, P squared is equal to E. That means P has order 2. Q also has order 2, and the same with R. So P, Q, and R. P, Q, and R. Okay. Apologies for the bad handwriting. I think that this is actually a good exercise. Um, about self-inverses, a very good thing to know is that every group that is of even order must have at least one self-inverse. And why is that? So, group of even order, if you exclude the identity element, which is order 1, then you're left with an odd number of non-identity elements. Okay, that means if we assume that all of every element has a distinct inverse, then we can pair them up. But you cannot pair up an odd number of elements, which means that at least one must be left out. And because if it's a group, it must follow the group axioms, then the one that's left out must be a self-inverse. That's a good thing to know. So you always know that you're going to have at least one self-inverse element. List the elements of the subgroup of G which are of order 3. Well, in this case, is going to be well, we don't know. Well, we know that this is abelian, so one of them is going to be of order 6, the generator. So if H is the generator, then H2, order of H2 is equal to 3, because again H4, and H6, which is just the identity. So let me find AB. Actually, we checked that earlier. A squared with, and then a to the 3. A squared is B, and B times A is E. So, and then if we check B, A, B, and also B squared and B cubed, same thing. So A and B are the elements of order 3. Now I'm very interested to know which one. Okay, that's interesting. There isn't a generator. Am I bugging? Shit. There is no generator. That's interesting. What? So this can't be isomorphic to C6. Surely, I'm missing something. B A B A squared B B A E. Oh, E is the identity. Okay. Okay. I'm interested to know what the marksman says about this. I might have spewed a lot of nonsense as of now, regardless. Okay, part two. Going back to part B. Multiplicative group H of all the six elements E and all the powers of C, where E is identity. Write down the order of each element, each of the elements. C3. So elements order. C3, C4, and C5. C3 is going to have order 2. Why? Because C3, then C3 squared, which is just 6, which is the identity. C4, we can do the same thing. C4 squared, which is C to the 8. But C to the 8, which is C to the 6, C to the 2, which is just C to the 2. And then C to the 2 to the 2 is equal to, was that correct? Um, yes, C to the 2 is equal to C to the 4. Wait, hold up, hold up. C to the 4, C to 4, C2, and then C4. Yeah, C2 times C4 is equal to the identity because this is just C6. Lastly, C to the 5. C to the 5 squared is C to the 10, which is C to the 4, and it's going to be a generator. I know this is going to be a generator because 5 is co-prime with 6. So this is 6, and this is, what did I say this was? 3. Okay, nice. Let me check. Let me find the mark scheme for this. I'm quite excited to see what they have to say. Um, this is question 1. Question 1. Let's. Okay, yeah. It is not commutative. Oh my god, I'm a complete idiot. This I'm a complete idiot. It isn't commutative. Okay, 3, that's correct. EAB, that's correct. 236, that's also correct. So if it's not commutative, then it's not abelian. So it's the dihedral group. Of course, it's a dihedral group. These are the reflections, and these are the reflections, and these are the rotations. I'm an absolute. How did I fumble this? This is actually embarrassing. Of course, there is no generator because it's not a cyclic group. And yes, it isn't. I should have checked this. It isn't symmetrical. Look at this. It isn't symmetrical. It is because this is an abelian subgroup. Okay, so I got fooled. This is why you got to check this. Not commutative. Okay. I just spoke for like 10 minutes about how this is abelian when it actually isn't. Okay. New question. This actually looks interesting. I don't think I've seen something like this ever before. Okay. Groups A, B, C, D are defined as follows. Write down the identity element for each group A, B, C, D. Okay. The set of numbers 2, 4, 6, 8 on the multiplication modulo 10. So this can either be a Klein 4 group or a cyc group. I think it's going to be a cyclic group. So it's not 2 because 2 squared is 4. It's not 4 because 4 times 4 is 60 and modulo 10 is 6. This will give me 6. It is not 6 because 36 modulo 10 is 6. And so it must be 8. And 8 times 8 is 64. modulo 10. No. 2, 4. 4 times 4 is 16. Modulo 10 is modulo 10. Yeah, it's 6. 36. 6 times 6 is 36. Modulo 10 is 6. 8 times 8, last time I checked, was 64. Modulo 10 is 4, which is not 8. Look, I'm going to come back to this. This is actually not good. Set the numbers 1, 5, 7, 11 under multiplication modulo 12. It's going to be 1. So here it's going to be 1 because 1 times anything is the same thing. Set of numbers under powers of 2 under multiplication modulo 15. It's 2 to 0. So I'm just going to highlight this. And then the set of numbers in the form 1 plus 2m, 1 plus 2n, where m and n and integers under multiplication. I can check this. They said 1 plus 2m, 1 plus 2n, multiplication modulo 15 is equal to, I'm not going to write the whole thing, 1 plus 2n, 1 plus 2n. And I mean, that's quite interesting because this is modulo 15. I can't really divide by, can I? Well, ease is just going to be 1, right? Yeah. The identity is just going to be the identity is just going to be oh, this is just multiplication. Okay, never mind. Module 15 is the one before. 1 plus 2m, 1 plus 2n times p is equal to 1 plus 2m, 1 plus 2n. That means e has to be 1. And 1 is equal to 1 plus 2, 0. 1 plus 2, 0. M and N are integers. 0 is an integer, I'm pretty sure. Yeah. So 1 and A, it seems to not have what do you call it? An identity. So I'm just going to write down the Cayley table for this very quickly. 2, 4, 6, 8. 4. 2 times 2 is 4. 4 times 4, 16, 6. 6 times 6, 36, 6. 8 times 8, 64. 4. 2 times 4, 8. 2 times 6, 12, 2. 2 times 8, 16, 6. 2 times 4 is 8. 2, 6. 4 times 6, 24, 4. 4 times 8, 32, 2. 6 times 4, 24, 4. 6 times 8, what was 6 times 8? 48, 8. 8 times 4, 32. And this is just 8 again. So 6 is my identity element because it's unchanged. So in this one, I kind of had to. I wonder if there's a faster way to get the identity. I think I'm just being stupid. Determine in each case whether the groups A and B, B and C, and A and C are isomorphic or non-isomorphic. Okay, A and B. Well, I could write down the Cayley table for B, and if there is the same pattern, then it has to be isomorphic. But there are only 2 groups. So for groups of order 4, I'm actually going to write this down. Groups of order 4, there is 2 possibilities. They're up to isomorphism. They are either cyclic, C4, or every element is the self-inverse, and that's known as the Klein 4 group, which I think is V the letter. Um, so to check this, all I need to do, I know that group, this is a cyclic group, and I'm sure about this time around because it's clearly symmetric. Otherwise, if it isn't, something was wrong. So C4 is isomorphic to, actually it's better to write this way. A is isomorphic to C4. Now, if 5 squared is the identity, then 5 squared is identity, 7 squared is identity, 11 squared is identity, then this isomorphic Klein 4 group. If it isn't, then it must be isomorphic to C4, which means it's isomorphic to A. So to check this, 5 squared is 25, modulo 12 is 8 plus 5, 8 plus 5 is 8 plus what is 8 plus 5? 13. So it's 1. Okay, and 1 is identity. Then 11 squared is 121, modulo 12, 121 modulo 12. That's going to be, let me get my calculator. It's going to be again 1. Okay, and then 7 squared is 49, which is modulo 12 is 1 because 48 is a multiple of 12. So yes, so B is isomorphic to V4. That means A is not isomorphic to B. Pretend this says isomorphic. Okay, that's first one done. Then to say B and C. Okay, we know that B is isomorphic to V4. So, and C is a cyclic group. C is isomorphic to C4. Therefore, B and C are not isomorphic. And it's quite obvious because C is literally in this form, and this is clearly a cyclic group generated by 2 to the 1. So yeah, so B and C are isomorphic. That's quite easy. Easiest 5 marks of now. A and C. A and C are isomorphic because A is, so A and C are isomorphic because both are cyclic groups. And there is one only cyclic group of order 4. So I'm actually quite happy with this. Um, okay. Prove the closure property for D. What on earth is? Oh, D is the funky one. Okay. D. Okay. I'm thinking actually. So for all M and N, not such that M and N, P and Q, which are integers, I'm going to take 2 to the M, 1 plus 2 to the N, times 1 plus 2P, 1 plus 2Q. This is 1 plus 2P, 2M, 4MP over 1 plus 2Q plus 2N plus 4. That's not QQN. Now, I need to write this in the form. This is my form that I need to write it in. I'm going to use different letters. This is the form I need to write on. So 1 is going to stay there. This is 1 plus 2 P plus M plus 2MP over 1 plus 2 Q plus N plus 2QN. And this is part of my set S. I'm just going to call this S. So it is closed. Good. Now last part. I don't think I need to show the question to you guys as well. Elements of the set that are combined under addition. State which of the four basic group properties are not satisfied. Justification is not required. I'm so happy. Quite obviously, the inverse. The inverse is what? And in addition, the inverse is minus that. Plus, actually no. Associativity. I think that's satisfied. I don't know. If it isn't associative, if it is associativity, that's not satisfied because that's so annoying to check. I'm gonna go by exclusion. One is not the identity. Zero is the identity. Um, and to get zero as the identity, m has to be minus a half. Yeah, and which is not an integer. So identity is not. There is no identity. Okay, and that's going to be my answer. It says which of the four basic group properties are not satisfied. Is it? Do I need to say there's more? It is closed. I think. I don't think it's closed. No, it isn't closed. It's clearly not closed. I think. Not closed as well. Not closed. The inverse. I mean, there is no identity. There is no inverse. And I don't even want to check associativity. I'm just gonna go to the marks. Oh hell no! I just shut down OneNote. I'm an idiot. Okay. I'm just gonna get OneNote up. Is it up? It isn't up. It is up now. Yes. I need to check whether I'm right. It's question 8. Um. Oh, the mark scheme. These mark schemes are actually quite good. I think, in my opinion. Okay, let me just put this here. Okay. Um. What did I say? 6 we're right, 1 right, 1 right, 1 right. So we're right for part 1. So A, okay, A is not isomorphic to B, B is not isomorphic to C, and A is isomorphic to C. So that's correct. Again, I think that was quite good. Easy 5 marks, not easy 5 marks, satisfying 5 marks. I don't know why they just drew the Katie table. That was completely necessary. Closure shown, fine. They have an interesting. What did I say here? Odd times over odd times odd over odd is equal to odd over odd earns full credit. I think that's a special case. That's interesting. Closure is not satisfied. Identity is not satisfied. Okay, so I was right. Okay, good. That feels good. Let me see how many questions I have. Oh my god. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 24 questions. 24 questions left. Okay. Um, my exam is tomorrow. It's almost midnight. I might be a bit cooked. Um, okay, I'm just gonna see if I'm still recording actually. I am still recording. 38 minutes. Oh gosh. Okay. A cyclic multiplicative group G has order 12. The identity of element of G is E, and another element is R with order 12. Write down in terms of E and R the elements of the subgroup G which is of order 2. Explain briefly why there is no proper subgroup G in which 2 of the elements are E and R. And then part B, a group H has order M and P where M and P are prime. State the possible order of proper subgroups H. That's an interesting question. Okay. Part A, when I read it first time right now, I don't think I digested anything that they said. Start group G has order 12. Identity is E. and okay, R is the generator. Okay, write down in terms of E and R the elements of this. Okay, this is going to be E R squared cubed to the 4, 5, 6, 7, 8, 9, 10. What? R to the 10, R to 11. Explain briefly why there is no proper subgroup of G in which two of the elements are E and R. Um, which two of the elements? Explain briefly why there is no proper subgroup in which no proper subgroup of G in which two of the elements are E and R. I mean, surely. Oh, because by Lagrange theorem, I don't know if it's I have to invoke it. Possible proper subgroups of order 6, 4, 3, and 2. It can't be 2 because that's generated by R to the 6. Can't be 3 because it's generated by R to the, hold on, 4. Can't be 4 because it's generated by R to the 3. And it can't be 6 because it's generated by R to the 6. Okay, so you can't have possibly a subgroup of order 2 with R and E because, I mean, it's not closed. Yeah, it's not closed. Not closed. This is not closed because you have R squared, which is not part of ER. But this is the only possibility. Okay, part B. Okay, I'm going quite fast now, so I'm happy. A group H has order M and P, where M and P are prime. State the possible orders of proper subgroups of H. By Lagrange theorem, which states that the order of a subgroup must divide the order of the group. M and P are your possible orders because they are factors of M and P. Let me check the mark scheme on this. Let me check quickly the mark scheme on this. I don't have a mark scheme for this. Uh-oh. Oh, I do have. Do I? Yeah, I don't have a mark scheme for this, sadly. But assume I'm right. I mean, I'm pretty sure I'm right. Okay. The operation this on real numbers defined by that. Oh, I've never seen this before. Show that this is not commutative. I'm just going to do it here, actually, sort of going down to the line pages, a bit necessary. Is A B. Actually, I can just give a counter example. I think A and minus one. Sorry, 1 and minus 1 is just 1. Minus 1 and 1 is minus 1. Hence, not commutative. I'm sure I need to do more than this, but I don't know. This is associative, so we need to consider all B and C, which are real. I'm not gonna. I always put the 2 dots, which is wrong. I need to show wrong place to put brackets is equal to A, B, C. A, B is this, which is, that's going to be annoying. This, I think. Yeah. Right hand side is, and this is, which is just, yeah. determine whether the set of real numbers under this forms a group. So it is associative, closed. Yes, it is closed. You can't have complex numbers out of this, so it is closed. Can't be asked to write down the whole thing for closure. Identity, the identity element is just one. Is it one? Yeah, it is. No, it's not one. Because before I had a counterexample. A so A E is equal to A, and so my identity is I need to write down, is going to be 0. No, 0 is not my identity. My identity is going to be it's just this. No, it's not. It is this, yeah. Yeah, this is my identity. Inverse, yeah, I mean, it's gonna have an inverse. Oh, we can't be asked to do this. Yeah, let's say just go in reverse. And then yeah, so it's gotta be a group. I'm so lazy. I'm not functioning well. Yeah, so it's a group. Is it a group? Uh, well, let's just say it's a group. You know, I don't know if I have marks in this. I don't know if it's worth doing. I'm just gonna move on. Um, okay, okay. This looks interesting. In this question, G is a group of order n, where n is between 3 and 8. In each case, write down the smallest value of n if G is cyclic, 3. If G has a proper subgroup of order 3, 6, by Lagrange's theorem. If G has at least 2 elements of order 2, 2 elements of order 2. The cyclic group, so 4, I think it's 4. Cyclic group has 2 elements of order 2, I'm pretty sure, because if H is generator, H2 has order 2, H4, not H4, H3 is generator, H1 is generator, so it's not 4, it's, I don't think it's 6, it is 6, it is 6, yes, because the dihedral group has reflections, which are order 2, are order 2, and has 2 of them, at least 3 of them, so it's at least 2. And the cyclic group of order 6 has, if H is generator, H3 is order 2, and H2D4, please be order 2. It's not that, no, 5, 6, 3, no, it isn't. It's not, it's gotta be 8, yeah. Because 6 has only, the cyclic group of 6 has 1 order 2 elements. Okay. Another group has the same order as G, but it's not isomorphic to G. Write down the possible values of M. Okay, 3 is unique up to isomorphism. 4 has 2 possible, so we already discussed this, the abelian group, the cyclic group, and the Klein group. So 4. Then you have 5. 5 is unique up to isomorphism. All prime numbered orders are unique up to isomorphism. So 7 is ruled out. 6 has a dihedral group and a cyclic group. 8 has actually, I think, 5 groups, 3 abelians and 2 non-abelian, and 8. Okay. Yeah. Yeah. I don't think you need to know about the composition, like the possible orders of 8 for orders of 8. I'm pretty sure it's 3 abelian and 2 non-abelian. But regardless, let's move on. Question 7. I don't think I'm halfway through. I need to go faster. Declaration this. I already did this question. I'm pretty sure I've seen this before. Let me see how I'm doing on time. I might have to do a part 2 for this. And how long have I been recording for? 51 minutes. Oh fuck. Crazy. I was about to swear. Do I continue? Why do I do this to myself? Okay, I can do this. The operation star. Have I checked the masking for the previous one? No, I haven't. I should do that. This is okay. I'm gonna do this quite quickly. Yeah, so it's 3, 6, 4, and 6. What? Ignore. Wait, hold on. That the marsham's got interesting stuff. 3, 6, and 4 has 2 elements for the 2. What? What? That's not. Wait, what? And ignore 8. Ignore all 8. Why and well, what? Another group has the same order as G, but it's not isomorphic to G. Rather than possible values of N. Hold up, what? I need to check with my teacher because I'm pretty sure you can have 2 groups of order 8 and not be isomorphic to each other. Okay, I'm gonna have to check this. I might. I'm gonna check with my teacher. And if it is, if I am right, I'll crash out. Has 2 elements of order 2. Has at least 2 elements of order 2. Well, yeah, the Klein group definitely has at least 2 elements of order 2. But the cyclic group does not have at least 2 elements of order 2. Unless I'm crazy. Yeah, it doesn't. E's identity h squared h cubed 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 e h cubed e h to the 5 h to the 6 h squared. Yeah, this is the only term that's order 2, so it's not possible. What? Okay, I'm contesting this as well. This is I gotta be right. This is not true. This is not true, unless I am not reading something. This has 2 elements, at least 2 elements of the 2. The cyclic group order 4 does not have at least 2. Okay, I disagree with this. I might be wrong. I will check on this and probably write a post correcting myself if I'm wrong. But I don't think I'm wrong. Because good I checked that. But yeah. 7I. The operation star is defined by x star y, x plus y minus a, where x and y are real numbers and a is a real constant. Prove that a set of real numbers together with the operation star forms a group. Okay. For Lx and y, for all xy, x star y is equal to x plus y minus a. Now, x plus y minus a is a real number. I think I just have to state this and it'll be fine. Hence closed. I don't know. Then the identity elements. This might be my last question I do because I'm generally asleep. I did just wake up as well. So kind of this might be a good way to tire myself out. X plus e minus a doesn't matter. It's commutative, so it doesn't matter. I think. Which is equal to x e minus a is equal to 0, e is equal to a. Okay, so the identity is a. Identity exists. My handwriting is getting worse and worse and worse. I am writing a touchpad, so is equal to the identity, which is a. X plus x1 minus a is equal to a is equal to 2a minus x. So, and this is a real number, therefore, in all elements have inverses. Associativity. Can we just assume it's associative, please? I cannot be asked. Okay. Let's say I prove associativity. Blah 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 blah. Hence associative. I cannot be asked. It's almost midnight, and I've got an exam tomorrow. State with a reason whether the group is commutative. It is commutative because I can just I can literally show it. Prove that there are no elements of the two. Actually, this is an interesting question. Um, to show that there are no elements of the two, I need to do x star y squared is equal to the identity, which is a. And to show this is not possible, assume this exists. X plus y minus a. Actually, is this x. This is 2x minus a x. And this is just 2x minus a plus x minus a, which is 3x minus 2a. And we're saying that this is equal to a. 3x minus 2a is equal to a. 3x is equal to 3a. X is equal to y. X is equal to a. So which is the identity, which is identity. Hence, no elements of order 2. That's a good technique to know. So contradiction, because we need to say this. Let's assume they mean no elements of the two, and especially excluding the identity, which is order 1. The operation, what that is defined as that, where x and y are positive real numbers. So it's basically that. By giving a numeric example in each case, show that two basic group properties are not necessarily satisfied. I so cannot be asked. Positive real numbers. I think with inverses might be the case. The inverse might not be satisfied. Okay, let me see what the next questions are, depending on. Oh, that's such a good one. Complex numbers. You know what? You know what I'm gonna do? I might wake up early tomorrow just so I can record the next ones. But these are good practice questions. They're not too heavy. These are actually good. I might, even if my exam's finished, I might sit down and record myself doing this because I think group theory is very fun. But yeah, I mean, it's 1 hour. My computer cannot handle me recording that much because again, my computer's on life support. So while I pack away, I'm just gonna waffle for a bit. Now, Extra Pure is absolutely my favorite maths module out there. It is just the best. I think if anyone wants some advice, wants to do Extra Pure, past papers are the bare minimum. Um, I think what you need to do is like part of the hassle is to go online and look for resources or make your own resources. It's very important that you're diligent with that. Doing past papers, doing the set papers, practice papers, doing the AS, that's just the bare minimum. That's what like you want to do to get an A. It just doesn't mean anything because people, I mean, this year they came out complaining about do I put my camera on? Can't really be asked. Um, People were complaining about what do you call it? The exam. So I do UCMI. And people were saying, "Oh, it was nothing like it was absolutely nothing like the past papers." Um, well, it doesn't have to be. The maths was the same. Uh, that might come out as rage bait, but I mean, I don't think you should rely on that as much. You just need to be good, and that comes from like a lot of practice. There's a trend with my year. All the papers so far have been have been very time pressured. Mechanics was very hard in my opinion. Statistics was I'm so happy about statistics. But that was there was consensus amongst my peers that stats was a weird paper and very time pressured. Usually you can finish a stats paper in like 40 minutes, but it wasn't exactly the case with this. The very last question was a very interesting chi-squared question, which I might do eventually. But yeah, and extra P, I'm just expecting the most horrendous, like the most algebraic. The paper is already algebraically heavy, but I'm just expecting the most outrageous thing, and I'm predicting you're gonna have recurrence relations of second order non-homogeneous or homogeneous with complex roots. I think that's an easy way that a lot of people might lose marks. And if they want to make the paper algebraically heavy, doing that might be a good. If they have a recurrence relation with like words, like a word problem, like they have a scenario, I am actually going to like get up and like I don't know headbutt an examiner or something. Like I'm actually going to cry if I see a question like that because I absolutely hate worded questions. um, Eigenvalues, eigenvectors. Last year there was the nasty, lambda is equal to 1. What does that mean? And there was a bit of a proof question. I'm hoping we don't get this year. We get more like Katie Hamilton theorem, algebra wise. Given enough time, I mean, you can always check your answer. That should be good. Group theory, I mean, I think that's a place they can make things really nasty. But again, there is not so much content there. What else is there? Multivariable calculus. This is what I think is going to get really nasty, and I'm happy with multivariable calculus. I did a lot of. I should have done practice as well. I mean, like in this video, multivariable calculus. Um, but I think that actually that's what I'm going to do tomorrow morning. Just go over multivariable calculus, because a lot of people might do the mistake of focusing, like obsessively focusing on group theory. Um, because it is. I mean, fair enough. It's the most new maths we've seen, but I think MVC recurrence relations they can get pretty hard as well. I think I've waffled for an hour straight. I'm just gonna stop, go to bed, relax. Yeah, and hopefully the exam, God willing, tomorrow goes well. I think we're just gonna stop yapping now.